Welcome back to the Electric Machine Design course. This is Jim Hendershot again, ready to give you lecture number 4, which is intended to cover the practical design aspects for electric machines, and we're going to include some design steps. I've given many lectures and workshops and tutorials over the years on electric machine design, and this is a set of steps that I have used in these presentations. So let's just take a look at some of these. I realize you can read them, but we'll read them together, and I'll go over some of the points that are important with these. The most important thing, of course, is to review the specifications, which are the requirements of the machines you're supposed to design. And it's not, but included in the specification is the certainly the output power required and all the characteristics of that, rated power, peak power, and if there's anything having to do with peak power, what's the duty cycle of that power? Is this a continuous duty machine, intermittent duty machine? And if you're supposed to, like traction applications have are required to produce peak power for accelerating or hill climbing, things like that. So the characteristics of that are very important, particularly from the thermal aspects. Got to know what the voltage is, because current costs a lot more than voltage, whether it's in the motor or the inverter. And what efficiency goals are required, and what cooling methods are required, and what's the envelope, the environment look like, and the mounting, and are there any heat sources that, like frequently a motor might be connected to a gearbox or a transmission or an engine, an IC engine or a jet engine, and so which is producing the most heat? Is the heat coming from the electric machine, or is it coming from the turbine engine? But once those things are known and a clear understanding is in hand, then the most important, I should have capitalized this next one here. The most important thing is to size the machine. And the sizing is somewhat related to the type of machine, but the principles of sizing are the same. And we're going to go into great detail, and we have a whole lecture dedicated to sizing, and so that's done by some long-standing practices. The configuration of the machine, radial gap, axial flux, radial flux, transverse, and how it's packaged and mounted, machine configuration itself. Then, of course, we base this on tried and true, known sets of data on the torque per rotor volume and the air gap shear stress, and standards on electric loading, current densities, and magnetic loading. Then the next step is to pick the materials required for this machine design. And by materials we mean active magnetic materials, not materials associated with mechanically packaging the machine, although those materials do come into play when you get into the thermal aspects of the design. But there's a lot of choices of lamination steels to be made, and not too many choices with conductors. Aluminum or copper is about your only choice. But there's certainly a big choice and selection of magnetic materials, and some of the packaging requirements of these materials, insulation systems for the conductors, and adhesives for holding magnets onto rotors, or rotor retention methods. You can also replace laminated cores with sintered cores. There's a lot of new materials available for magnetic materials made out of sintered parts. Allows you to achieve quite complex shapes of magnetic cores that would be difficult to achieve through a stamped, punched, laminated structure. Then, of course, there's significant progress has been made in recent years on potting compounds and encapsulating materials. And we're going to talk about that at great length as well. The semiconductor industry namely companies like Intel, who've been packaging transistors for years now, and microprocessors. There's millions of transistors in a microprocessor, and the density is so high that they are not able to extract all of the heat generated by this constant switching of the gating of these transistors. They're not able to extract all the heat from the metal plate that's on the bottom of the pack. So they have to take heat off the top of the pack, which is the pack's encapsulated with some sort of thermoplastic or epoxy, usually thermoplastics. And you've noticed your Intel microprocessor it's a big flat pack thing, and it's got aluminum fins all over the top of it, a little fan. So what that means is they're taking a lot of heat off the surface of that thing. Well, those materials typically had a thermal conductivity of no better than 1. Water is 0.56 or 0.7, 0.56 to 0.6 is water. That's the thermal conductivity of water. So the insulation materials, the varnish used in motors and regular plastics and things like that have a thermal conductivity of 0.12, 0.13. So that's not very good to take the heat off the top of the an injection molded encapsulated pack. So there's been a lot of work done by the thermoplastic material suppliers and the epoxy suppliers to fill these materials with all kinds of oxides and nitrides that will improve this thermal conductivity. And so those materials have been developed by Intel suppliers for packaging their microprocessors, are very useful for motor engineers to use to pot encapsulated stators with to increase their torque density. So we're going to talk about that. And then, of course, you have the choice in this whole design process to pick the type of motor. However, this isn't always a choice. Sometimes you're asked to model a motor of 2 or 3 different types just to compare the results, the cost, the weight, the torque density, the performance, to help them pick which one. But many times it's your specification dictates up front that which type of motor that you have to design for our design steps. So, but frequently you do have to compare machines. The permanent magnet AC motors or brushless motors driven by sine drives, and they can be surface mount or interior. Now this is very common to if you've been told that you have to design a permanent magnet synchronous machine, but tell me, do a design comparison on an IPM or an SPM and tell me which one I need, which one is best for us from cost and performance point of view. And frequently you have to work with your inverter engineer on this as well. And other times people ask you to, well, can I replace our existing motor with an SR or induction motor or a reluctant synchronous machine, RSM? So, and then after you pick the motor and you complete your magnetic design, then you have to predict all the results here. And I guess I went backwards here. I should have gone from materials to the initial design tasks involved. After you pick the materials, involved the number of poles, the number of slots, the rotor and stator dimensions, the details of the rotor stator dimensions, and back EMF wave shapes, winding design, flux distribution in the circuit, and finally how many turns per coil do you need? And so then after you've made all those decisions, that's when you have to predict the results by predicting torque speed curves and current voltage results, efficiency, and check your gap loading, PSI in the air gap, torque speed curves, peak power, torque speed curves, and what the back EMF and most importantly what the losses are. Losses are a very daunting task. We're going to have a lot more to say about that, And the last thing you do, I guess, is compare these motors. And but for now, I've used the previous slide for most of my courses, but I made a special one for this course to go into some more detail about all this that we just talked about, because maybe the steps should be a little different for the purpose of this course, since we're comparing three machines. So we have to review the specifications, and the most important thing to do is to size the machine. That has to be done up front. You know, none of the design theory courses you ever took, or none of the analysis you do with MATLAB Simulink on models, or none of these exercises help you, even circle diagrams, none of those methods decide what diameter to make the motor and how long to make it, how big the rotor should be, and those are the things you got to decide as a machine designer. So you size it and select the machine type, and you have to select the pole number. Then the next thing you do is design the stator, and the stator. Once you've got this far, you could actually change rotor designs. You could actually compare these three rotors we're going to talk about with the same stator. You could do that. Some people are interested in doing that. Like, for example, if magnet prices continue to escalate in cost, maybe you want to use your automated motor for a car or a traction application as an induction machine for a few years, or a reluctant synchronous machine until the price of magnets come back down, and then maybe you want to put the permanent magnet rotor inside that stator. Or maybe you want to offer both at two different prices and two different performance levels. That's another thing that might be worth doing. So then when you get down to the designing the rotor to go with that, when you get down to design the stator to go with that rotor, you can look at all these different rotor types: the reluctant synchronous, the permanent magnet AC, brushless DC, and then of course this has an IPM or surface version. This is always surface, or the induction machine. And for any of those, all those, you have to complete the magnetic circuit cross-section. And what that means is determining, once you have selected the active materials and the pole number, you pick one of these PM machines, for example, you're going to know how much flux you have per pole, so then you have to design the lambs to have the right cross-section to carry that flux per pole so it's not saturated. In the case of the induction motor, your peak torque determines the maximum magnetizing flux and the maximum magnetizing current. So in the rotor design, you have to balance the cross-sectional area of the copper for the cage with the cross-sectional area of the steel to carry the flux for the peak torques. That's the key. And now in the case of the reluctant synchronous machine has flux carriers and flux barriers. And you want to have low flux density in the flux carriers, but to have low flux densities in the carriers, you're going to have too thin or too narrow or too ineffective of flux barriers. And if you don't have enough flux barriers, your saliency ratio will be too low, and you won't get much torque or torque density out of the machine, or power factor efficiency. So it's a matter of optimizing that. So you have to do a lot of reiterative designs to get the magnetic cross-section right. Then, after you've done that, you calculate the magnetizing flux for the induction machines and the RSM machine. You know what it is because you picked the magnet for the PM machines. Then it's time to design the phase windings. Pick the right winding pattern and the right winding configuration. Where do the actual conductors go in the slots? Where do you put them in the slots? You just copy somebody else's design, or do you design this yourself? And there's not much in that you can find in the literature about showing you how to do that. And then, of course, the next thing you do is solve for the machine results, the performance results, and there's two ways to do that by old classical time-proven equations. And you can speed that process up by using Excel or spreadsheets to semi-automate the use of those analytical equations, or you can buy software programs that have done that. But eventually, for some of these results, you're going to have to use finite element analysis. And so we're going to talk about finite element analysis versus analytical solution methods. And finally, you've got to do a thermal analysis and find out, list all your losses, identify where they are, what their magnitudes are, and then determine what the terminal or steady state temperature of all the key components in the machine, the active magnetic materials in the machine. You can't overheat magnets or they demagnetize. You can't overheat insulation systems or they fail. And of course you can't overheat copper wire either. So a thermal analysis is very important. There's software to do that, but you can use lump parameter methods for that, which have been used for many years. But all of those thermal methods have to be backed up by some sort of test validation. Doesn't mean that that's the only way that. What I mean by that is to do some analysis of some motors that you have some thermal data on, then use that to calibrate your model to use on the next one that hasn't been tested yet. So you really have to calibrate any lump parameter or FEA thermal analysis with some calibrate against the machines that you have some data on. And finally, you write a report on all this stuff. So here we've written out all these same steps in a list of 10 steps here. No, I don't think we need to go over them again. Let's see if there's any other points that come to mind. Establishing the number of poles is sometimes it's in your specification, but not always. It might be maximum, established maximum. Sometimes induction motor, if it's an induction motor and you're going to use it with a certain inverter that already exists, it might be specified. But I think the designer should always push his customer, his boss, his inverter partner. He should always push to maximize the number of poles. Always try to increase it, because what this does is this improves the torque density of the machine. Doesn't improve the power density, it improves the torque density of the machine. And there's a lot of controversy over that terminology. Some people talk about power density all the time. I can double the power density of any motor by doubling the speed, because power is torque times speed. But I can't double the torque density by doubling the speed. But I can double the, I can't double it, I can improve the torque density by doubling the number of poles. And the reason that is possible is because when you double the number of poles, the thickness of the yokes are cut in half. So there's several things you can do with that extra radial space. You can make the machine smaller, saving weight, mass, and inertia, or you can increase the torque density by increasing the torque itself, by keeping the OD of the machine the same and making the rotor larger in diameter by keeping the stator slots the same depth. You make the rotor larger in diameter by the amount you reduce the yoke thicknesses too. In the case of permanent magnet machines, when you increase the number of poles, it allows you to decrease the magnet thickness and use less magnet material. And so let's see, I'm looking at other. The number 6 here, select the number of stator slots and the phase winding. That's an important step that requires a clear understanding of what the choices are and why you pick the ones you pick. Many times the number one criteria is performance. If you want the highest performance machine, then you would use an integral slot per pole per phase. In other words, the number of phases must divide into the number of stator slots for a balanced winding. That goes without saying. So stator slot numbers have to, if for 3-phase motors, stator slots have to be in multiples of 3. So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, that sort of thing, and multiples thereof. Okay, now the final number of slots per phase can depend on a lot of things. If you want to have a very short end turns in a machine and low I²R losses in the end turns, you want to have the end turns real tight against the end of the core, you don't want them sticking way out, then you have to have a slot pole combination that's a fractional slot or integral slot, whereas the coil is wrapped around a single tooth. And a common one is a half a slot per pole per phase, which would be like a 6-slot stator, 4 poles. So 6 slots divided by 3 phases is 2 slots per phase, per pole. Oh, per phase. So divide by 4 poles, and you get a half a slot per pole per phase. So that's a fractional slot winding, but that's a winding whereas the coil is wrapped around a single tooth, so that the amount of copper in the end turns is no different than the cross section of what's in the slot. If you span multiple slots and you got a lot more copper there to mash down, it's going to stick out farther past the ends. It's harder to cool that as well. It's harder to cool the multiple slot winding. So manufacturing has a lot to do with it. If you want a real high slot fill and you want to automate the winding, then you almost have to use a winding where the coils are around individual teeth. Then, of course, selection of magnetic materials, active magnetic materials, is really a big deal. All the magnet grades and neodymium, the cost, versus ceramic. And if you use ceramic, it has such a low flux density, you have to have very clever magnetic circuits to be able to use it, where you can focus the flux and get the lines of flux you need. And once you know what the flux is in an induction machine or a PM machine, then we have to pick the number of turns in the wire gauge. And then once you've done that, another challenge, which isn't mentioned yet, but we're going to talk about it extensively, is the requirement to when you get down to designing a coil and you pick the number of turns, frequently let's take an example of a coil that requires 1 turn per coil or 2 turns per coil. So that single turn in that coil, if you made it out of a single strand or a single conductor, it would be so thick, so big, that it would be very hard to wind and insert and to make the external connections to. So it's very popular to use multiple strands in hand or parallel strands carrying the current. Well, when you do that, a big problem, a big design problem, a quality problem comes about because the current, if the current is not shared, if I have 1 turn per coil and I have 10 strands per turn, I have to have 1/10 of the current in each strand to have equal current density, or the lowest current density in the strands. But if for some reason or other, and there are a number of reasons why current will not evenly distribute itself through the strand, parallel strands, that's a design problem to deal with. And then there's Then there's the other one, whereas the current will, under some high frequency conditions, the current, due to what's known as the skin effect, the current concentrates itself in the skin, a layer of copper skin at the OD, and it doesn't penetrate the whole cross section. So the current density in the skin of the conductor where it flows is very high, and it's very low in the middle. So this causes overheating as well. Then the other one is where the current concentrates on one side of the conductor or the other. One side of the side of the conductor closest to the rotor air gap, the current's the density's maximum there, but on the other side of the conductor it's almost zero. That's called the proximity effect. So these things have to be dealt with and studied as well. Then finalizing the cross sections for the teeth and the yokes, and that's a balance between flux density and current density and losses. Many motors, the losses are a function of flux density and frequency. How many times a second you cause the flux to go from positive to negative, or you turn it on or off. You switch the coil on and off, so you magnetize or you cause the flux to collapse to zero. How many times a second? That frequency causes losses, and then the magnitude of the flux causes losses. So, and in machines, the frequency is not the same in the teeth and the yokes all the time. Usually, the yoke, particularly reluctance machines, the frequency in the yokes are higher than the frequency in the teeth. So that all has to be taken into account in calculating the core losses. Since the core losses are a function of frequency and flux density, you have to calculate the losses in the teeth and the yoke separately based on their flux density and their frequency. Since most machines can be used for motoring or generating, we have to make sure we understand that the efficient production for motoring, the most important parameter in our design that we have to keep in the back of our mind during this process is to produce the desired shaft torque at whatever speeds are needed. The most important parameter is the efficiency of that torque production. For generating, it's not torque production at all. It's the efficient production of electrical power. And if you have like for example, when you're generating, if you have some extra losses in the generator, even though those losses could cause the generator to heat up, that's not really an efficiency loss for the generator within itself. It's still efficiency loss in the flow of power, but the generator doesn't care if the prime mover has to produce some extra torque to overcome windage in the air gap, for example, or friction in the bearings. It doesn't care about that. That doesn't have anything to do with generating power, except for the thermal aspects of it. So in generating, the mechanical, the iron losses are considered mechanical losses. For motoring, the iron losses are considering electrical losses. Same as the ohmic losses. Now some machines, particularly brushless and permanent magnet and some induction, are used to generate and motors. For example, a starter generator for a jet engine. It has to act as a motor when it's cranking the engine to get it up to light-off speed before ignition and fuel is applied. Then once the engine ignites and it starts to motor itself, then usually this electrical machine is still motoring to get the jet engine up to speed as fast as possible. So both are motoring. But once it gets up to some higher speed, then the starter aspects of this electric machine switches over and it becomes now a generator. It's not motoring anymore, it's generating. It's generating electricity, and the prime mover, the jet engine, is supplying all the torque. Let's talk a minute about the classical design approach versus practical design. There's plenty of historical machine design workshops and courses that provide in-depth analysis of classical concepts, but in those classes there's usually insufficient time to teach you the practical machine design steps that are usually left up to the students or learn on the job after they get a job somewhere. Most college classes and professors don't teach us, and that's one of the main purposes of these lectures, is to fill in that gap, to provide the design process, the practical aspects of what we get as consultants. We get calls all the time from graduate students in universities all over the world that in their thesis project they have to build a machine, and they understand the theory better than I do, but they don't have a clue how to start the machine, and some of the problems they ask us to help them with are quite amazing. They're based on naiveness and nativity with respect to the upfront decisions they made to design and build a prototype. We see this a lot there's a lot of wind turbine projects going on around the world as master's and PhD thesis, and years ago it used to be hybrid vehicles, electric vehicles, solar vehicles, things like that. Now it seems to be wind turbine or energy related things. So these lectures are intended to help these people like that get started. Now, as we said before, as I said in an earlier lecture, I showed a picture of this magnet on the left that's an example of a bar magnet with a north and a south pole and with iron filings over the top of it. And what happens is if I had iron around that like you have in the picture on the right, all we can do when we calculate magnetic circuits, like you look at this picture here, and if we had iron here, we would assume, the point I'm trying to make here is we assume that the flux density, using classical analytical methods and analytical formulas, you always assume that flux densities are uniform in any given cross-section, because that's the only way you can design it. In other words, if I know that this magnet has 100,000 lines of flux, and I know that flux from that magnet has to go through across this cross-section, I divide this area into the total number of lines to get lines per square inch or lines per square millimeter, whatever the case is, and I assume that it's uniform across there, but it isn't uniform across there. The flux is highest in a cross-section where the magnetic reluctance is the lowest. In other words, all the fluxes, the length of the path determines magnetic reluctance. Short path has lower reluctance than long path. So the flux is going to tend to go around the shortest path. It doesn't want to go around the longest path because it takes more work, so to speak. Think of it that way, to go around a long path than does a short. To magnetize a short path takes less MMF than a long path. So there's going to be a voltage gradient across here. It's going to be higher there than it is there. And now, something obvious in this case, we have a tapered tooth here, so the same number of lines going through this tooth is going to be a higher flux density in this part of the tooth than that part of the tooth. So if I'm going to calculate the loss of this machine, and the other thing you notice is the flux density is not uniform in all these teeth. So if I have so much flux in the magnet, and I'm using an analytical method, I just told you how I'd calculate the flux density in the yoke. But how I'd calculate it in the teeth is I would take the cross-sectional area of the teeth, and I'd probably use the average, which would be right in the middle, And I'd multiply that times the number of teeth per pole and divide the total lines of flux from the magnets into by the total cross-sectional area. And so I'd get an average flux density of all these teeth in a pole, you see? But by using a finite element analysis, we find out that that's not the case at all. That parts of the circuit saturate, like these little sections saturate, these little sections saturate. Not all the flux from the magnet goes through the stator. So my hand calculation has got a big error in it in terms of the flux density in the yoke, and it's certainly got a big error in it in the average flux density in all these teeth. You can see because I've lost some of the flux. I even lose from saturating this. That reduces the saturation here, reduces the flux out there. So the finite element solutions give you a much more accurate representation of the flux distribution. And what is a finite element? Well, remember I told you I take this cross section, that's that dimension times the depth into the paper or the board or the screen, and that's my area, and I calculate the average flux density in that area. Well, what finite element does is it breaks all these areas up into finer little cross sections, little triangular cross sections, and it calculates the flux density in each one of those little things, and then it knits them all together to get a flux distribution throughout the whole cross section. And you'll notice these lines here are not, if you see a solution where the lines aren't smooth, then that means that it had to jump when it tied them all, when it knitted them all the flux densities together, when it knitted them together, it had to go along an irregular connections of all those little elements because there wasn't enough of them. So you can go to a higher order FEA solution which just increases the number of elements, and that smooths up these equal potential lines. It didn't really change the torque or the final result all that much, but it sure makes you think it does. It looks more uniform, and it certainly looks better in your report. Although having said that, you still can get some errors through too coarse of a mesh. A mesh is the picture of all the elements that you pick. You want a high concentration of elements in areas where you expect there to be saturation. Like you certainly want a lot of elements in the air gap. In the air gap, you'll probably make layers of, probably have 2, 3, 4 layers of elements in there, so that if you do a dynamic solution, if you want to rotate this rotor and resolve it at every new position, you want those layers to reconnect with each other to have a smooth transition of flux distribution through there as close to reality as possible. So the FEA method is really necessary for all IPMs. It's necessary anytime you're close to saturation. It's necessary to calculate Cogging torques and torque ripples. And if you have transverse flux machines, you need 3D solvers. But a machine like this, you don't need a 3D solver. 2D is good, except for thermal, you need 3D. So everything we said here that applies to a magnetic circuit and magnetic flux also applies to fluid dynamics, which is precisely what a thermal problem is. It's a fluid dynamics problem. And even though the fluid is air, it can be air or some other liquid. Air is really a liquid. When I was in high school, studied physics, I was taught there's 3 states of matter: gases, liquids, and solids. When I got into college and studied physics, I was taught there's 2 states of matter. There's liquids and solids, because a gas is just a loose liquid. It's a liquid with a very low viscosity. So, to summarize our machine design considerations, we certainly have to always consider manufacturing, and many times that dictates the design. a lot of times, like for example, an obvious example is that for low-cost manufacturing, the manufacturing people, purchasing people, and sometimes management, they want to use cheap magnets and cheap laminations, and they want real low slot fills of copper in the windings to make it easy to wind and not have any failures and have a very high throughput. But you see, there's a price to pay for all those low-cost aspects. Like these days, you've heard all these stories about high-efficient, premium-efficient motors. Well, premium-efficient motors are not low-cost motors. They're expensive motors. How do you make a premium-efficient motor? You use more expensive lamination materials that exhibit lower core losses. You put insulation on each one of them. You might even have to anneal them, post-process them after you stamp them. And then you stuff the slots full of copper. You use larger wire gauge or more strands in parallel to get the current density low. That's what reduces the ohmic losses and improves efficiency. The other thing you do, which you have to do, is have real short interns. So you wind the coils before you insert them. You wind them very tight, very short, so that the end turns don't stick out very far. But manufacturing people don't like that because it's slower, more tedious, and much more difficult to insert these shorter coils into the slots of the cores to get them over the teeth, to span the number of teeth they have to. So if it's an automated machinery, you can have jams in machinery. You can even break part of the tooling by trying to put short, tight coils in that just barely fit over the teeth. So, but if the volume is high enough, if you're in a market where the volume's high enough, then you can make new tooling and change the infrastructure and the whole manufacturing process to allow you to have important improvements in efficiency, high slot fills, and good materials. Some designs, some new designs that you might think of, and this is an important point to make in this series, I think, and that is that many inventors and designers of machines today come up with new, exotic, strange, off-the-wall configurations. And those are fine, and they have some features, but the problem is, historically, those kind of machines seldom, if ever, get into production because they require so much new infrastructure and new tooling and new thinking about manufacturing. So that's important to think of that. That's one of the difficulties with pancake motors or axial flux motors. Sure, they have very high torque density. They have a lot of wonderful features going for them, but nothing about the components or the manufacturing is like any other motor, so they're not standard. It requires all new tooling, all new infrastructure, and new assembly methods and everything. They have a whole different set of problems. So just because they have a higher torque density than a radial gap motor doesn't mean that they're are guaranteed to be successful. And it's a manufacturing infrastructure that's really killed them, I think. And the same, I think, it goes through for transverse flux machines. But transverse flux machines might have an advantage, as might axial flux machines, for large wind turbines. They might work for that. If you want real high torque density, you're going to have to use extreme cooling methods, like we already said, short end turns and high copper fill. Maybe even hollow conductors, maybe even heat pipes in the rotors. If you're talking induction machines, spray cooling on the rotors, spray cooling on the end turns of the winding. Larger machines have to have channels through the cores for cooling, because the thermal diffusion paths are so long that the sources of heat are such a long way from the place where the heat can be extracted that the copper will heat up before it ever transmits this heat by conduction through the mechanical parts out where it can be extracted. So cooling passages are put in between sections of the stator and the rotor core, and fancy pressurized blower systems to blow air, or even large machines even use liquid nitrogen and hydrogen, actually use hydrogen cooling. So some extreme cooling methods are required for high torque densities. Then, of course, we all know about the operating environments: hermetics, vacuum, nuclear, cryogenic, and extremely hot environments. You have to deal with those and use special materials. Sometimes that limits the type of motor you can use. Maybe a switch reluctance motor is an excellent motor to use for a real high temperature application at 750 degrees Fahrenheit or something like that. Might be a good choice for that. Another thing that's important is for safety or fault tolerance. That's an issue. A PM machine, if you got permanent magnets, you get a short in the windings, then you can't turn the back EMF off. You've got a short circuit current that flows, and that can cause a fire and cause death, all kinds of things. So fault tolerance, that's an important issue. Switch reluctance motors seem to have a big advantage for that. We can compare these some machine types: surface machine, AC brushless, internal machine brushless against induction. Here's a comparison that was done by these three gentlemen. This is an IEEE IAS magazine article that compared three of these machines. Induction motor right here, a surface, and an IPM, and this is one of the few studies of this I've ever seen. So this would be, I think, be useful for all of you that have this question in your mind. You can see what the full load currents are and the full load efficiencies are, and the base frequencies. So, and they're all approximately the same voltage. I don't know why they're different. They're not exactly the same. This is a 75 horse motor, 1800 RPM, common stator core with different windings. They all have the same stator core, but a different winding. So you see, it's I say the induction machine's quite impressive here. I think it's very impressive. To the current's higher, of course, because you had to, with these two machines, the current's lower because the magnetizing comes from the magnets with both of these machines. Now it's interesting, the IPM requires higher current than the surface machine does. The one thing they should have put on here, maybe, I'm pretty sure this was a copper rotor. They should put somehow relate and weight the cost of the copper rotor versus the cost of the surface PM motor versus the IPM, because usually the IPM motor is going to use less mass of magnets than the surface magnet, because it gets a torque component from the saliency between the permanent magnets, which we'll look at later. It gets a reluctance torque. The IPM is really a hybrid between a PM machine and a PM synchronous machine and a switch reluctance synchronous machine, because it gets a reluctance torque, and that's why the full load current is almost as high as the induction motor, because you had to have extra current to magnetize that the salient poles, and that was done effectively by using power to saturate part of the magnetic circuit around the poles, around the magnet poles, to force the torque through the saliency part of the poles. So that's kind of effectively equivalent to, since you had to magnetize that part of the circuit for the reluctance torque component, it's almost the same current as what was required to magnetize the current for the induction machine. And then, of course, the IPM was higher efficiency, though, probably because it got so much more output torque and power because it had the saliency torque component. Now, as far as the RSM machines, I don't have personal experience with this type of comparison, so I've offered for you a plot that's been published in the year 2012 by Alan Bradley, or not Alan Bradley, ABB, the Swedish big Swedish motor company that bought Reliance and Baldor, and they've just released a whole product line of these reluctant synchronous machines, and so they've plotted efficiency versus power for their product line, and they've taken their standard induction motor product line. They use the same stator, and they've replaced the stator with their synchronous reluctance rotor. They've replaced the induction rotor with a RSM rotor using the same stator and their line of inverters, and plotted this efficiency due to reduction in losses. There's no real magnetizing current required for this. So that gives you a good indication of whether that curve has enticed a lot of people to look at reluctant synchronous alternative to permanent magnets. The machines with non-salient pole rotors are induction and PM, and some common characteristics of them here we'll summarize again. You can use 3, 6, 9 phases. They use the same stator punching for use for all of these. You need a new rotor design for each one. The active materials lamination grades are the same. Phase windings can be the same. The PM synchronous need not have the same number of poles in the rotor and the stator where the other two machines do. That might surprise you. Induction machines always have the same number of poles in the rotor and the stator, but that's because they're induced there. And the RSM has to have the same number of poles in the rotor and stator because it's a synchronous machine. Now, people keep calling the permanent magnet brushless machine a synchronous machine, but you can make a strong argument that it's not a synchronous machine, because with this machine, it's very unique. I can have a different number of poles in the rotor than the stator. That's going to surprise a lot of people. For example, a 12-slot stator and a 10-pole rotor, permanent magnet machine, you cannot generate 10 poles with the stator with 12 slots and 12 coils. It's impossible. But I can wind that motor with 6 coils, 2 coils per pole, 180 degrees apart, 6 coils, every other tooth has no coil on it. And I've only really created 4 poles per phase, but that runs very nicely with a 10-pole permanent magnet rotor. So that's an interesting difference. But in all of these configurations, the first thing you have to start with is a scaled motor cross-section until you work that into the final design. Long before we ever had computers, the motor designer had to start with a piece of graph paper, a couple of triangles, a straight edge, a ruler, and a compass. And he would start with, we'll talk about sizing, but going through that sizing process, he would draw a sketch of the machine, and with lots of years experience, you can begin to pick diameters of rotor given the stator. You could pick tooth widths and yoke thicknesses and magnet thicknesses and things like that, just based on your experience. But to use that experience, you have to use a scaled layout or a scaled drawing to do it with. So that's very useful for machine design. The designing of the components, the steps for that, we've already looked at that in general, but specifically the most important thing to start with is to size the machine based on the duty cycle, the specification, performance requirements, and how you're going to cool it. And as we've said over and over, you got to select the number of slots, poles, and phases, and then design the laminations, the cross sections, and the materials. Calculate the iron losses. And iron losses, we're gonna cover a lot about that. There's a lot of problems with iron losses. Historically, the giants of the electric motor industry, they would use the iron core loss data published by the electric steel manufacturers, and they would use that data to calculate the losses in the machine, and they would build the machine and test it, and they would find that the losses would be 100, 200% higher than what they calculated. So it seems like the data has a lot to be discussed and to be thought about. It's not uncommon to use a calibration or a fudge factor just to whatever losses you calculate, you double it to be safe for iron losses. Some people will go 300%, 200%. I use 1.5 to 2.0 calibration factors. And as far as installation class versus temperature, you got to meet industrial specs. All the methods of cooling machines, we've got some lectures on that. That's in some respects that's a lost art. Years ago, they used to perform some fantastic liquid and forced air cooling, which is only published these days in very old textbooks you could only buy used. There's really not much in print on it. We've got some reproductions in our last lecture of some of those techniques we'll show you. Remember I said in the earlier lecture that since the switch reluctance machine doesn't use the same stator as these other three machines, we haven't considered in this comparison, but there's so much interest with switch reluctance now that I felt it was necessary to put a couple slides in here and discuss it at least, so that you know a little bit about it and how it compares with the other machines. First of all, let's summarize some characteristics. These switch reluctance machines have a very simple structure. The rotor can be punched out of the stator and a progressive die, and the stator looks like an internal gear and the rotor looks like an external gear. Simple as that. There's combinations of slots or teeth, stator and rotor teeth combinations that will work with 2, 3, 4, 5, 6 phase machines, and outside of those they won't work. So there's combinations that you have to use, and it's all about the attracting force in the air gap of the rotor teeth to the stator teeth, or let's call them poles. So the design's all about how to maximize that with the least amount of energy input or current. So the machine is very simple. The coils are simple. They're wound around the stator teeth. There's no windings on the rotor at all. Some early proponents of these machines said the rotors are cool, that they don't generate heat. That's not really true. They do generate heat due to eddy current and hysteresis losses, because as you rotate this and attract those poles, you're magnetizing those poles and demagnetizing those poles, and you're actually even reversing the polarity of the poles as you switch and go around. Not on every switch, but at least once per rev, you're reversing the polarity. So that causes hysteresis losses. Now, there's, in this particular case here, the one at the top, you have only 2 rotor poles that are attracted at a time. The lower picture, you have 4 rotor poles attracted at a time. So that the frequency of switching, or the commutation frequency, or the DVDT frequency, is different in the stator yoke, the stator teeth, the rotor teeth and the rotor yoke. It's not the same in any of those. So in calculating the losses, you have to solve for the flux density in each one of those four cross-sectional areas, and then use whatever frequency it is to calculate the losses. So it ought to be obvious that the frequencies are higher with switch reluctance than they are other kinds of machines, so you tend to use thinner, more expensive lamination materials. And because of the saliency of the machine and the attraction of those poles, see that when a pole in the rotor comes around, is attracted to the stator, the thin section modulus of the stator yoke deflects, acts like a big spring. So on the top, as that thing rotates, that stator is trying to elliptify. It's trying to change from a circle to an ellipse because those poles are attracted. And then when you turn the phase off, they're released. So that causes that yoke to, that circle to vibrate between a bigger and smaller ellipse all the time until that settling time rings out and settles out. And then you fire the next one, and you have this again on the next pair of poles. Now the one below has four attracting points, 90 degrees apart. So instead of this trying to make itself elliptical as it is commutated, it becomes more like a square. So just on the face of it, the one at the bottom is quieter. If everything else is equal, same torque, same diameter, same voltage, everything, the one at the bottom is going to be quieter than the one at the top because it's with the same yoke thickness. The deflection is way less. It's much stiffer because of the arc length between 90 degrees and 180. So the effective Stetson modulus against that deflection makes it quieter. So that's one of the big drawbacks of reluctance machines is their audible noise, and that's why Professor Miller used to say that every switch reluctance motor is equipped with a gremlin that lives in the stator, and he's got a little mallet, and every time it commutates, why he raps on the OD of the stator with his mallet, and that's what you hear. But I guess that's not very funny. Sorry about that. So the principles of producing torque we've talked about several different ways, but it's quite different from the salient pole machine versus the non-salient pole machine. As you can see, the non-salient pole machine, due to the Lorentz forces, you get an attraction and repulsion effect from each side of the coil. Each coil has two sides to it, so one side of that coil is giving you a north pole, and one's giving you a south pole. So whether you're motoring or generating, that pole is being attracted to the pole in the other member, and it's also being repulsed in the other member. Where the salient pole machine, there's no repulsion, it's only attraction. So you might think, well, that means you're going to get half the torque density out of a salient pole machine. Well, and there's some truth to that. That's why to get comparable performance on a salient pole machine, you've got to drive the iron into saturation around the poles. It's the only way you can make up for the fact that you're not. This was evidenced by a famous paper by two IBM guys by the name of Paletko and Chai. They were advocates of reluctance machines for step motors because they didn't require any magnets, and IBM didn't want to use magnets in their step motors that they use for their printers and a lot of their computer peripherals when they used to make all those things. Remember, they were the leaders in computers for many years, and they made all their own peripherals. And Paletko and Chai discovered that a reluctance machine could compete with about anything if you drive the circuit into saturation around the air gap. It essentially doubled the torque output by driving it. And saturation is against all principles of magnetism and magnetics. But with a reluctance machines, you overcome this repulsion attraction deficiency with a salient pole machine because you only have attraction. And you make up for the repulsive force by by real high forces in it, doubling the attraction force for what it was out there. So flux linkage is where it's all about. The torque per amp is produced in the air gap between the rotor and stator from the flux linkage between the rotor and stator. And so that what that means is that after you've sized the thing, the first thing you got to do is figure out how much flux you got. And with a PM machine, you do that by picking a magnet and estimating what the load line is. In other words, the ratio of the air gap to the magnet thickness, and we'll go over that in detail. That determines the flux density from that magnet in the circuit. You multiply that times the magnet area, and that gives you the flux. So you got the flux. So now all you got to do is figure out how many ampere turns you need for the electromagnetic circuit. Now, in the case of an induction machine and a reluctant synchronous machine, since they don't have any magnets, you start with an air gap flux density that you assume, and then you solve and see what it takes for magnetizing current and number of turns, ampere turns, to achieve that flux density. So because you can't start an induction motor design without some assumed flux density, so you assume it's somewhere between 0.65 and 0.85 Tesla in the air gap, and I think 0.8 is a good place to start, really. For you might get it a bit higher. Pretty tough to get over 1 Tesla in the air gap. So now you got to adjust the circuit to carry that flux for all these 3 machines by figuring out what the cross sections are, and you have to balance that with the cross section you have available for copper, because once you know what the ampere turns are, you know what the current is, you know what the current, how many turns, how much space you got, what the current density is. And the performance analysis of this requires iterations. That's why computer simulations save a lot of time. Takes what used to take a design months to get done, you can do in a week or days now using computers. And don't forget that we have to predict the temperature with the thermal rise. I just threw this little picture in here to reiterate what Lorentz forces are all about, just to know when I'm done with this lecture. It doesn't really have much to do with what we talked about in this lecture, but it certainly shows the what's happening there in the air gap for the force on. When I studied this, I didn't study forces on conductors. I studied forces on particles. That's how I was taught Maxwell's equation. It took a while to get that translated. I had a chief engineer that was very good that translated the forces on particles to forces on poles, magnets, and wires. Okay, thank you very much for your attention.